For whatever reason, there's not just one fundamental theorem of calculus, there are two. Don't worry, there are just two, no more than that. So today we're going to talk about the second fundamental theorem of calculus. So let's kind of lead up to it first. Let's just consider this function. If you notice, this has two variables in it. It has a t and an x, and the function is actually a function of x. So if you think carefully about what this function does, this function actually would find the area under the curve t squared plus 5 from 0 to x. So in other words, when you plug 1 into this function, the answer is going to be whatever the area under t squared plus 5 is from 0 to 1. Or if you plug in 11, it's going to tell you the area under the function t squared plus 5 from 0 to 11. So really our x just determines how big our interval is. So we can actually find this as a more normal equation. We can take the antiderivative. We would get 1/3 t cubed plus 5t from 0 to x. Then plug in the top number minus the bottom number. Well, we just get 0, so I'm going to not worry about that and just erase it. So that probably looks more like what you're used to for a function, and that is that if we just plug in an x, we just do that. There's no integral involved. But this function still does the same thing. This is just another way to write what we had originally. So if I plug in 1, it tells me what the area is of t squared plus 5, and so on. I'm not going to go through all that again. But let's say now that we have this function, they asked for f prime. I mean, we're in calculus. Why wouldn't they ask for the derivative, right? Okay, well, so we take the derivative of our function. 3 times 1/3, we get x squared plus 5. Now I want you to look carefully. Compare this to what we started with at the beginning. It's the exact same thing, except we've traded the t for an x. And that's going to happen every time. What the second fundamental theorem of calculus does is it makes it exceedingly clear and very explicitly that if you do the derivative of an integral, those are inverses of each other. And so the result is basically just going to be what you started with. Again, the whole goal here is to relate derivatives and integrals to each other. And frankly, I feel like it's more obvious, at least to most people, how that works in the second fundamental theorem of calculus than how it is in the first. So let me write that out for you. The second fundamental theorem of calculus, okay, it also has the stipulation that we have to be continuous on the interval. But basically it says that if you take the derivative of an integral, then the result is just the function you originally had on the inside of the integral with x plugged in. Because basically what happens is this derivative cancels out this integral. And so they cancel each other out, and it just leaves you with the f of t. But because we've had to plug in the x and the a, that's why we now have f of x instead of f of t. If you notice, it doesn't stipulate what a is. It doesn't matter what number is on the bottom, because the result is always just going to be just f of x. And here's why. If you go back to the one we did before, let's say I had plugged in, 1 right here. So then I had 1 minus 1/3 times 1 cubed plus 5 times 1. Right, so we get a number there. I think it's going to be like 5 1/3. Well, if you think about that, when we take the derivative like we did in the next step to go from here to here, what's going to happen to that 5.3 repeating? It's just going to disappear because the derivative of any constant is 0. So that's why it doesn't matter at all what number's on the bottom, because once you plug that number in, your result is a number, and when you take the derivative of a number, it just gives you 0. So that's why you can have any number you want in the bottom there. So I think it's time for some examples. let's start with f of x is equal to the integral from 0 to x of 4t cubed minus 2 dt. And then they say find f prime of x. Anytime you see them ask you to take the derivative of an integral, you need to connect in your brain that that goes with the second fundamental theorem of calculus. Anytime you're asked to take the derivative of an integral. Okay, so all you have to do, it's this hard, is you plug x in here, and that's your answer. That is what f prime of x is equal to. So this is about as easy as it can get. Let's try another one. Say f of x is equal to the integral from 0 to x, or actually let's make it something other than 0. Say it's 3 of t squared plus 5t over t plus 7. And then they say find f prime of x. Or they may even put a derivative out front, kind of like we did back before. They may ask just for the derivative of that, put something like that out front. Just be aware, anytime they ask for the derivative of an integral, that you're going to use the second fundamental theorem of calculus. All we do for the second fundamental theorem is just get rid of the integral sign and plug the x in everywhere we see a t. So our answer is that we get x squared plus 5x over x plus 7. Very simple. We didn't have to worry about any weird quotient rules or anything like that. We just did it. So I want to say one more time, don't forget that the number down here makes no difference whatsoever. It doesn't matter if it's 0, 3, 103. It's not going to have any effect on your answer. Alright, but these can get a little harder. Let's, for example, try this one. Find f prime of x for f of x equals the integral from 0 to x squared of sine t dt. So you can probably tell what's going to make this a little more difficult, and that's the x squared in the boundary instead of just x. Okay, so let's actually do this one the long way, and hopefully that'll make it clear how we're going to do it with a shortcut or with using the second fundamental theorem. Okay, if I actually solve this integral, I take the antiderivative, I get negative cosine of t from 0 to x squared. It gives me negative cosine of x squared minus negative cosine of 0, or negative cosine of x squared plus 1. Okay, so that would be another way to write our f of x. I've just solved the integral that was on the other side. Now to take the derivative of that, the derivative of negative cosine is positive sine, and I'm going to have to use the chain rule here and do times 2x, because that's the derivative of the inside. And then the derivative of 1 is of course 0, so it disappears. So if you notice, I still plugged x squared in for the t, but I also had to multiply by the derivative of that t, which was x squared. So I had to multiply by the derivative of what I plugged in. So it comes from the chain rule. You can see that we did it the long way. That's how it's going to work. One way you can almost think about it is it's like, okay, well, we're replacing t with x squared, so then the derivative of t would be 2x. And you've got to plug that in for t and that in for dt. Now you may ask, well, why didn't we have to do that before? Well, before, our t was just equal to x, and the derivative of that would just be 1, so there's no reason to add that on. So for these, there's two steps. Plug in the variable for t, and then multiply by the derivative of what you plugged in. And this really only matters if you're plugging in something other than x. It still holds true if you're plugging in x, because the derivative is just 1. But mainly this is something to focus on when you're plugging in something other than just x. So I'm going to give you a couple more examples of those. Let's let's say they ask us to find f prime of x for f of x equals the integral from 0 to 2x plus 2 of t cubed plus 5. So for this one, we take what we have up here and plug it in for t. That's going to give us 2x plus 2 cubed plus 5. Now I need to multiply that whole thing by the derivative of what's on top, which would just be 2. Because if what we're plugging in is 2x plus 2, its derivative is simply 2. And then if you want, you can go ahead and distribute that through. And for the purpose of these problems, there's no reason to simplify any further than that. You don't need to cube out the 2x plus 2 or anything like that. But make sure you multiply the entire thing by that derivative. Okay, if you look back here, there were parentheses to start with before you multiplied by the derivative, so make sure you do the same thing here. Okay, one more example. Let's say they ask this, derivative of square root of t dt. Okay. So again, take what you have up here, plug it in for t, so we would get the square root of sine of x, and then multiply by the derivative of what you plugged in. So we have to multiply by cosine x. And that would be our answer. So to practice these, I want you to turn to page 286 and do number 81 through 91 odd. But for now, you can omit number 87.